Okay, so for the last video in this tutorial, we're going to be showing how to link the optimization engine with our finite element model and our parametric model to create an optimized part. So what we're going to do here is we're going to first go into our part. There's one more item that we need to add into it, and that's a measure of the amount of material that we're using. Ultimately, this optimization is going to be designed to minimize material and also minimize the deflection of this particular point where we're loading it. We've already added in a parameter using that sensor to show what that displacement is. And now we have to add in a parameter to understand what the volume of this material is. So I'm going to go into my link, and I'm going to double click this optimized shape to bring us into the part workbench. I'm going to add in a parameter. Click on f of x, new parameter of type, and we want volume. And hit that and hit OK. So go into parameters, and you should see a volume listed there. Double click it, and we're going to right click on this and say edit formula. And so far we've used measures to measure like an area of a surface or a line or whatever. In this case we're going to be using part measures because we're measuring a solid part object. So we want smart volume, and then double click on part. Oh, sorry about that. Make sure you're clicked in between the parentheses. Click on part body so it fills it in, and then click OK. Click yes, and now you'll see the box is grayed out and it's linked to the volume of that particular solid body, which is right around 0.15 liters. We're working in liters in this, again, because you can change the units at Catia. You can work in whatever type of units that you want. In this case, we'll be constraining the ultimate volume. The value will be in liters. Let's just hit OK. Let's hit Control S for save. All right. So now what I'm going to do is I'm going to go back up to my analysis manager. Okay. And so we want to make sure that we're highlighted in this. And now we're going to create our optimization. So we're going to go to Start, KnowledgeWare, Product Engineering Optimizer. Okay. And what you'll notice is you should have a new part of the tree here that says Relations. If that doesn't show up, go to Tools, Options, and then you're going to want to go down to Analysis and Simulation, General, Show Parameters and Show Relations. We want to put those into the tree and hit OK. By default, when we clicked on this, it also hit our part. I'm going to unhide it. Right click. Okay, so now we want to create a new optimization. Let's click on optimization on the right here. Looks like a little target. And so let's start by setting up the constraints. Click up at the top, you'll see problem. We want to do only constraints. I'm going to click on constraints, and I'm going to click new. So the two constraints we're adding relate to that displacement of the edge of our model, or the where we're loading it, and the material amount. Let's start with the displacement. So we want to minimize this displacement. I'm going to click on the parameter itself. It automatically fills it in our window up here, and I'm going to say equals 0 millimeters. So the double equals is that's setting the target of 0 millimeters, and we're going to hit OK. So it adds it in here. It tells you it's not satisfied because we're getting some displacement. Of course, this will probably always have some displacement here. We're never going to get it down to 0. And then we're going to create the second constraint. We're going to hit New. We're going to click on the plus next to our link here to expand that tree. And we're going to click on Parameters and this volume. And our constraint here is going to be, we want to use less than 0.05 liters of plastic. So this is approximately 1/3 of what this shape is now. So we're going to expect this to be quite a bit minimized. I'm going to hit OK. So that's our constraints. Now we have to set up our problem. So the problem is we're gonna add in these free parameters that lets it make this whole shape malleable, right? So I'm going to click on Edit List, all right? And we have a couple parameters in the tree that we're going to be using. Hole diameter we're going to leave because we're not changing the bolt hole diameter. That's going to be set to that 1/4 inch bolt. The corner radii, we're going to let it modify that. Ultimately, if you remember, that also adjusts this outer offset of that curve. So that's definitely something that we want to add in. If we click on it, it's going to highlight it on the left side of this window. We're going to add it to the right. So then that's a parameter it can modify. We're also going to let it modify the thickness of the shape. And ultimately, we want to let it control those original edges of the shape. If you remember, these edges here and how we created them with these offsets. Go ahead and click on the geometrical set that you made, and you'll see those 3 parallel edges. Those really modify the thickness of this thing at the midpoint. And we want to let it flex and adjust that. So what we're going to do is here, we're going to set this to, we're going to click on that offset. You'll notice it highlighted here, and we're going to move it over. So we're going to repeat that for these other 2 parallels in this tree, as well as for the inner shape. I'm going to unhide that. So the other 3 parallels that we created. Okay, so we should have all 6 of those parameters listed here. And we're going to hit OK. Now, I'm going to go back and just hide these so we're only looking at that solid body again. So the other option that we have here is that we can set a range for these things. So Catia is relatively smart that you can just let it run without setting a range. What happens is usually optimization takes longer. Also, if you let it run free, it might put in parameters that ultimately cause your parametric model to not work correctly. If it set this radius too small or something, if that radius was smaller than this hole, the thing wouldn't work. So ultimately, we want to constrain those parameters a bit. I'm going to set the corner radii. I'm going to edit that list. I'm sorry. I'm going to say edit ranges and step with that selected. And so I'm going to set the smallest range to 5, and let's make the biggest 30. And hit OK. The thickness, I'm going to also constrain that. I don't want it thicker than 3 millimeters. Now, if you remember, that's half the thickness. So you just have to keep that in mind. So that would ultimately make a shape about a 1/4 inch thick by setting it to 3. And we don't want it to get more than 60 millimeters thick. That'd be pretty big. So I'm going to enter 30 into here. Okay. And then I'm going to also set limits on these outer shapes. So actually, let's take a look at those. First, I'm just going to hit OK. That's going to save our optimization in this in the tree. Let's go take a look at that back at our parameters for outer shape. So I'm going to hide the part body and go into outer shape here. Let's take a look at this parallel, for instance. So this parallel curve, we can modify it. I probably don't want that curving in, but you know, maybe a shape like this on one of the curves would somehow be effective. So I don't want to push it too far in, but let's just hit cancel. And so I'm going to give it a range that ultimately may have this inner curve and that outer, or the outer curve and the inner curve somehow overlap. That's okay, because if the model fails, Catia will just ignore that run and keep moving on. So then the inner shape, let's take a look at what that is. Again, it's a similar kind of offset. We can have it pull inwards and outwards. So let's go back to our optimization and limit those parameters. So for the outer parameter shapes, we can make this window bigger so we can see what we're working on here. So these three parallels for the outer, I'm going to hit edit range. And I'm going to say the small range is -5. I'm going to let that go up to, I'm going to let it go pretty big if it wants to. So -5 to 30. And we're going to do that for all three of the outer. Now you may find that you need to tweak these later on or something. That's okay. You know, it's always kind of a work in progress how you sort of constrain the optimization, but you don't want to over constrain it so that it can't find the optimum solution. Okay. So then let's take a look at the inner parameters. I'm going to let these flex inward a bit more. So we're going to say -15 millimeters and then all the way up to 5 and hit OK. So okay, what it was doing right there is it was saying the parameter that I had entered was actually out of that range, and it's going to adjust it for me. Hit OK. Same thing. Okay. All right. So we've set those limits, and again, some parameters within these options might fail. It'll just keep running. What I tend to do is, if I've given it a lot of leeway, I want this conversions to be set to slow. Otherwise, it might fall into a poor solution too quickly. Now, what I'm going to do here is I'm going to set the maximum number of updates. You can set all these numbers much higher. Essentially, the number of updates is how many cycles it'll go through. The next number is how many times it'll fail at finding a better solution before it stops the optimizer. And of course, you can just set a time limit. In this case, I'm going to set a time limit of 1 minute because we don't want it to run too long for this video. And we just want to make sure that it's working at this point. Okay, so then I'm going to do save optimization data and then with visualization update. I'm going to hit OK just to make sure that it's saved in there. And before we run anything, we're going to go ahead and hit Control S for save. And it's going to save analysis. We're going to hit OK. One other way you can save, just a little side note here, is go to File, Save Management. You'll notice all your parts that you have open at the time are in here. It's also showing where you're saving your analysis results. You can change that. Maybe if you have a big, fast external drive or something. But all the files that are open right now, it's showing how they're saved. Okay, I'm going to go ahead back into my link. I'm going to unhide the part body. I'm going to hide these other shapes. We don't need to look at those for now. Okay, and even the supports. We don't need to see any of that stuff. Okay. Now, let's double click on that optimization, kind of get it into a good view here. And then the last thing we're going to do is we want to make sure we save the optimization data. What that's going to allow us to do is it's going to put that into an Excel file, and later on we're going to be able to click on the results, computational results up here, and look at the various options that it created. So I'm going to make sure it's on slow. It's maximum time of 1 minute right now, and we're going to hit Run Optimization. It's asking me where to save the file. I'm just going to call it optimization data. Hit save. It's going to take it a second to start running. This is normal, especially since I'm recording video at this point. So now what it's going to do is sometimes you'll see updates up here in the 3D window. Depending on how fast your computer is, this is just running on my laptop, so I'm probably not going to see the updates. But what you will see is each time it's running the finite element model in the corner here, it's updating. So you should see the two numbers here changing as we go. And those numbers are the volume of the material, which it's already lowered, and then the finite element model displacement. Now, in this case, if we watch this here, it hasn't improved this in 9 cycles. So it improved the first one, and now it's not finding a better solution quite yet, which is okay when especially when you're doing slow convergence. It's bouncing around a bit. That's okay. We just wanted to make sure that it was actually running. That's what I tend to do first. So what we can do is we can also see, now that we've run it, we can hit computational results. Now we can see the parameters that it was adding in for all these different options. We can also click on this and say apply values to parameters. This may be one that doesn't work though. Let's see what happens. Okay, so that was a design iteration. Quite different than what we started out with, but it also wasn't an improved case. Let's see what this one looks like. Slightly different, a little bit thicker. So now what I'm going to do is I'm going to pause. I'm going to let this run for a little while, and then we'll see what it gives us after a bit of time. Okay, so I let the optimizer run for about 45 minutes. It made it through approximately a few hundred iterations. I'm sorry, close to 1,000 iterations actually. And it came up with this as the final result. Now, this was the current solution that it had found at the time. That doesn't necessarily mean it's the most aesthetic solution or the solution we want to ultimately choose. You know, we can let the parameters, we can let the optimizer iterate longer. We can try different options. I actually switched it to fast as we were going here as another option. You know, there's a number of different things that we can do with different algorithms, and I urge you to try, you know, different constraints, not different constraints, but setting up the problem differently with different ranges for the parameters, etc. If we look at the optimization window now, actually the computational results tab is no longer grayed out. If we take a look at the parameters listed here, this is the different free parameters that it tried. And so if we look at this window, we can see, let's see, it got just close to 1,000 different parameters. If we click on any one of these and say apply values, we can see what it actually tried. and it'll rerun the solution. Now this might have been a very slight difference in the iteration, but we can take a look what it did and then also look at what the displacement was. I think this one still, to be honest, has quite a bit to run, but another thing we can do is we can select parameters to show how different curves adapted as we went. So if we look at the two constraints and then maybe the thickness of the object and hit parameters to be displayed and hit OK and say show curves, now we can see how it iterated through those different parameters. By selecting on the different curves, it'll rescale the graph, and it allows us to just kind of get a real idea of, you know, where these parameters were trending to, so we can understand, okay, well, as it made it thicker, you know, how that affected the different output parameters. You can also change, there's a number of different ways to visualize things. I'm not going to go over all those here. If you take a look at the different options here, you can adjust how you're visualizing those graphs. This ultimately can be used to change the problem and update the problem. We're not going to change the constraints, but we can change how we constrain the problem. Okay, so one thing I want to note that I did update in between optimizations is, I'm just going to hit OK. If I go into the restraints, I actually updated this restraint after thinking about it some more. One thing you'll want to note is instead of the clamp, I went with a user-defined restraint, and I put one of those in each of the spots that we had a clamp. Zoom in here a bit. I'm going to double click on this. And so I'm actually restraining it in translation in all three axes, so in the X, Y, and Z direction. And I'm restraining it in rotation in two of the axes. So what I'm not restraining it is in the X axis, which would, if I turn this on just so we can see what that is, that's rotating about the axis this way. The reason I'm not restraining it is because ultimately that bolt going through there will not restrain this pivot point. It's going to be, even if it's pretty tight, it'll probably allow it to move a little bit in that direction. Okay. So I did the same thing for the lower connection as well. It still gives me a fully constrained solution because I have this point and that point constrained. So what it does is, though, it frees up these different members to act how they will more so in real life when we test this whole piece. Okay, so that concludes the optimization video. I look forward to seeing your results.